In this chapter, we will discuss how ionic compounds form, and how metallic bonding in metals affect its properties. All elements in a group have the same valence electrons. The chemical properties of an element are largely determined by the number of valence electrons. Valence electron is defined as an electron in the highest occupied energy level of an atom. The number of valence electrons is determined by the element's group number. For the representative elements, which are the group A elements, the number of valence electrons is equal to the group number. For example, all elements in group 4A have 4 valence electrons. Helium is the only exception to this rule. Helium is in group 8A but has only 2 valence electrons. The electron dot structure is a diagram that shows the element with valence electrons as dots. Atoms like to have their orbitals completely filled with electrons. That's why noble gases are very stable. With the exception of helium, the general rule for noble gases is having 8 valence electrons, which lead to the octet rule. The octet rule states that in a chemical reaction, atoms gain or lose electrons to acquire the electron configuration of a noble gas. In this table, the electron dot structure of some elements in group 1A to 8A is shown. In group 8A, the noble gases have 8 valence electrons, with the exception of helium. Scientists discovered that atoms tend to form compounds in a way that allows them to have 8 electrons in their highest occupied energy level. A set of 8 is called an octet. A cation forms when an atom loses electrons. Let's have a look at the sodium atom. Sodium belongs to group 1A, so it has 1 valence electron. It can lose an electron to form a cation with charge +1. You can show the ionization by writing the complete electron configuration of the atom and of the ion formed. Notice that the electron configuration of the sodium ion is the same as the electron configuration of a neon atom. Both the sodium ion and neon atom have 8 valence electrons, in other words, the octet configuration. Using electron dot structures, you can show the ionization more simply. Let's look at the transition metal cations. The charges of the cations of the transition metals may vary. Iron may lose 2 electrons to form iron 2+, or it may lose 3 electrons to form an iron 3+ cation. Some ions formed by transition metals do not have a noble gas configuration. Copper is an example. To achieve the structure of the noble gas argon, a copper atom would have to lose 11 electrons, and to achieve the structure of the noble gas krypton, copper would have to gain 7 electrons. Ions with charges of 3 or more are not common, so there are exceptions to the octet rule. A copper atom can still form a cation. If a copper atom loses its 4s electron, the copper cation has 18 electrons in the highest occupied level, so all the orbitals are filled, which is relatively stable. Such a configuration is called a pseudo-noble gas configuration. Here is the electron configuration of the copper atom and the copper cation, after losing a valence electron. Note, copper is an exception to the Aufbau principle. Instead of having 2 electrons in the 4s orbital and 9 electrons in the 3d orbital, as the Aufbau principle predicts, it has a completely filled 3d orbital, with 1 electron in the 4s orbital. This is because copper achieves a more stable configuration by moving an electron from the 4s orbital to the 3d orbital, resulting in a fully filled d sublevel instead of a partially filled one. This is possible because the energy difference between the 4s and 3d orbitals is very small, so the stability gained by having a fully filled sublevel outweighs the energy required to promote an electron to a higher energy level. When an atom gains 1 or more electrons, it becomes negatively charged because the number of electrons is greater than the number of positively charged protons. The name of an anion of a nonmetallic element usually ends in "ide." For example, a chlorine atom forms a chloride anion. Chlorine belongs to group 7A, so it has 7 valence electrons. It can achieve the noble gas configuration by gaining an electron, as shown here. A gain of 1 electron gives chlorine an octet and converts a chlorine atom into a chloride ion. In the table we can find some other common anions. The diagram below shows how both the chloride ion and the argon atom have an octet configuration in their highest occupied energy levels. You can use the electron dot structures to write an equation showing the formation of a chloride ion from a choline atom. An ionic compound is a compound made up of cations and anions. Sodium chloride is an ionic compound made up of sodium cations and chloride anions. Ionic compounds are electrically neutral. The positive charge of the cations is equal to the negative charge of the anions. When sodium and chlorine react to form a compound, the sodium atom transfers its one valence electron to the chlorine atom. So, sodium and chlorine combine in a 1-to-1 ratio, and both resulting ions have stable octets. Ions are charged particles that exert electrostatic forces on one another. Ions with the same charge repel each other, and opposite charges attract. Cations and anions have opposite charges, which leads to attraction and the formation of a bond. An ionic bond is the bond that holds ions in ionic compounds together. You can describe the composition of substances by writing chemical formulas. A chemical formula is an expression of the number of atoms of each element in the smallest representative unit of a substance. A formula unit is defined as the lowest whole number ratio of ions in an ionic compound. Example: in magnesium chloride, the ratio of magnesium cations to chloride anions is 1-to-2, in other words 1 magnesium 2 plus ion to 2 chloride ions. The formula unit is shown here. Let's do an exercise. What is the formula unit for the ionic compound formed by potassium and oxygen? First, write the electron dot structures for the potassium and oxygen atoms. Clearly, potassium must lose one valence electron, and oxygen must gain 2 electrons to reach a noble gas configuration. So, the ratio will be 2 potassium ions per oxygen ion. The chemical formula for the ionic compound is written below. Here are some properties of ionic compounds. Most ionic compounds are crystalline solids at room temperature, and have a high melting point. The crystal structure of an ionic compound is determined by the arrangement of its ions. Sodium chloride and cesium chloride both form cubic crystals, but the arrangement of its ions within each crystal is different. Ionic compounds can conduct an electric current when melted or dissolved in water. Metals are not made up of neutral atoms. Instead, metals consist of closely packed cations and loosely held valence electrons. The valence electrons of atoms in a pure metal can be modeled as a sea of electrons that can move freely from one part of the metal to another. A metallic bond is the force of attraction that holds free valence electrons and metal cations together. The motion of electrons in metals explains many of its physical properties. Metals are ductile. Metals can be drawn into wires by forcing the metal through a narrow opening. Metals are malleable, which means that they can be hammered or pressed into shapes. Metals are good conductors of electric current, because electrons flow freely in metals. Metals are crystalline, the atoms are arranged in very compact and orderly patterns. Below, the arrangement of chromium atoms, gold atoms and zinc atoms is shown. There are many metallic items, but very few are made out of a single kind of metal. Instead, most of the metals we use are alloys. An alloy is a mixture of 2 or more elements, at least one of which is a metal. Alloys are important because their properties are often superior to those of their component elements. Here are a couple of examples. Brass is an alloy of copper and zinc. Bronze is an alloy made up of 7 parts of copper and 1 part of tin. Stainless steel is an alloy made up of iron, chromium, carbon and nickel. The most important alloys are steels. Most steels are made of iron, carbon, and small amounts of metals, like chromium and manganese. Steels have many useful properties, such as corrosion resistance, ductility, hardness, etc.